So I'll be talking about energy and entropy, and in particular how they appear in classical physics, in general relativity, and then in semi-classical gravity. And the reason why we're shooting toward semi-classical gravity is because, as you'll see, semi-classical gravity is the framework within which certain aspects of cosmology, in particular dark energy, are most naturally posed and studied. So because I've been working my way through Proust recently, La Recherche du Temps Perdu, this seems like a very Proustian topic to me, I hope you'll see. So that was the inspiration for the section titles. So I'll begin with just a very quick review of the frameworks of quantum field theory on curved space-time and semi-classical gravity, just to get us in the mood and to show how it is that the study of lambda very naturally fits into this framework. I'll review energy and entropy in classical physics, energy and entropy conditions in classical GR, and the Sodom and Gomorrah of semi-classical gravity. And then because I was supposed to talk not about I had promised to talk not about probability yesterday, but about matter and gravity and matter and geometry and the differences between them, such as it is. I hope I'll be able to get to that at the end and say a few things about it. But also, I remember yesterday there wasn't a lot of time for questions after the probability talk. So before I launch into this, are there any questions from yesterday about probabilistic reasoning in cosmology? Okay, I take it that means that everything I said was perfectly lucid and clear, and everyone understood every single word, since there are no questions about it. I had no idea I was such a great lecturer. That's fantastic. Okay, so let's get started. So our two best theories of the world today are general relativity, our first best theory. It's valid from middling to largest spatial and temporal scales, and from near perfect vacuum to super dense matter distributions. Its most characteristic feature is its it represents space-time geometry as a dynamical entity evolving dynamically along with matter, both affecting how matter evolves and how matter evolves affecting the space-time geometry evolution. There are no quantum effects. It's, in that sense, a purely classical theory. And what's also perhaps most characteristic of general relativity is the fact that the causal structure, because of the dynamical nature of space-time, can become extremely complex and really quite bizarre and weird. Y'all have probably heard of closed time-like curves, a path through space-time where an observer continually moves forward in time, but ends up returning to the exact same space-time point from which he started. It's very difficult to make physical sense of that, but it's a perfectly valid situation in a space-time geometry. Things can get even much weirder than that. And it turns out, as we'll see, the possibility for this extreme causal weirdness can affect how it is we try to model quantum fields and quantum effects in space-time. So our second best theory, quantum field theory, which the framework within which physicists have developed the standard model of high-energy particle physics. It's valid for mesomolecular and smaller matter distributions at the smallest spatial and temporal scales, and for the highest energy scales and lowest energy scales we've been able to probe. It is posed on a static flat space-time geometry, Minkowski space-time. It does not incorporate gravity. And by the way, it's important to realize that this statement does not imply this statement, because people do try and construct effective perturbative theories of quantum gravity in which there's a spin-2 massless particle called the graviton, and that's almost always formulated on Minkowski spacetime. So the fact that the standard model of particle physics doesn't incorporate gravity does not follow from this. It's an extra feature, if you like, or a problem, a bug in the standard model. And of course, I take it everyone here is familiar with at least some forms of extreme quantum weirdness that are seemingly inconsistent with certain features of general relativity, primarily with superposition that causes the problems. Entanglement, while to my mind much more characteristic, that's the truly characteristically weird quantum phenomenon. Entanglement per se doesn't really cause problems with general relativity. It's superposition that causes problems. Because the matter distribution, the stress energy tensor in general relativity that couples to the Einstein tensor, it forms the Einstein field equation, the stress energy tensor, it makes no sense to put a quantum system that is in a superposed state and equate it to a classical curvature tensor. There are many fundamental tensions and inconsistencies, seemingly, between general relativity and quantum field theory. Almost all of them derive from one basic fact, or if you like, two basic facts that are juxtaposed to make one basic fact. So it's that in the dynamical equations in the space of states in quantum theory are linear. A Hilbert space is a vector space. It makes sense if I have two states, I can add them. That's why we get superpositions. The space of states and the equation for GR is extremely nonlinear. This conflict, if you like, almost all the problems that are involved in trying to put general relativity and quantum field theory together in any way, whether it's semi-classical gravity or trying to construct a program of quantum gravity, this conflict lies at the heart of almost every single problem. And we don't know how to resolve it. So the simplest framework to try and study how it is that quantum matter behaves in a general relativistic spacetime is the framework of quantum field theory on curved spacetime, as it is called. And given what I've said about the seeming inconsistency, tensions and perhaps inconsistencies between the two frameworks, it is perhaps surprising to learn that there is, in fact, a completely consistent, rigorous theory of quantum fields living on a classical relativistic space-time background. So you fix background classical space-time geometry. You know, Minkowski space-time is boring. That's where QFT is always formulated, but it is a general relativistic space-time. But we're interested in curved space-time, so Schwarzschild space-time, FLRW, and you then represent a quantum field kind of living on the space-time, but not coupled to the curvature by way of the Einstein field equation. So you treat the quantum field as test matter, as it's very often called, or it's a free field. So the stress energy content of the quantum field, because we think every matter field has stress energy, we ignore the contribution of the stress energy content of the quantum field to the curvature of the spacetime. It's exactly the same thing that you do in Newtonian gravity when you're modeling, say, an orbit of the planet around the sun, and you ignore the gravitational contribution of the planet. You treat the planet as test matter, as a test particle, and only worry about the gravitational field generated by the sun. It's exactly the same thing. And even though the quantum field, the stress energy content, doesn't contribute to the curvature of spacetime, nonetheless, there is non-trivial interaction. Because remember the wonderful aphorism of John Wheeler, space-time tells matter how to move, and matter tells space-time how to curve. So in this case, matter isn't telling space-time how to curve, but space-time is telling matter how to move. The dynamical evolution of the quantum field is governed by the affine structure of the space-time. So it's not that you can just choose any old classical space-time geometry and any old quantum field and any old state and slap them together. They have to be, the state of the quantum field has to be consistent in a certain precise technical sense with the affine structure, the geodesic structure of the classical space-time. But we want to truly have a fully coupled interacting theory of quantum fields and space-time geometry. We want to have not only the quantum field being guided by the affine structure of space-time, we want not only space-time telling quantum fields how to move, we also want the stress energy content of the quantum field telling space-time how to curve. And so the way this is standardly done is by use of what's called the semi-classical Einstein field equation. So we still are treating space-time purely classically. It's a classical general relativistic space-time with all of the classical curvature tensors and measures of curvature. But on the right-hand side, instead of a stress energy tensor for classical matter, we construct for the given quantum field that we're postulating lives in the space-time, we construct an operator, a quantum operator, that represents the quantum stress energy content of the quantum field. We take its expectation value in the state that we think the quantum field is in, and we set that equal to the classical Einstein curvature tensor. And of course, we have the cosmological constant term, dark energy. But as I discussed, God, was it yesterday? I'm really bad at chronology. I think it was yesterday. Or no, maybe it was the day before. Anyway, at some point, I showed you how it is that we think that many people think we should be able to derive the cosmological constant, dark energy, as the contribution of the 0-point energy, the vacuum energy of quantum fields to the stress energy content of space-time. And that's what we do. So whether we, that little sigh shouldn't be there, ignore that. So whether we think that this term comes from the 0-point energy of the quantum field, or whether we're using some other model of dark energy, like a so-called phantom field, or K quintessence, or dilatonic dark energy, any of your favorite models of dark energy, they're all fundamentally quantum. And we know by the homogeneity and isotropy of the universe that the expectation value for the mass energy of whatever this quantum field or quantum effect is should be, the expectation value of it should be a constant. And so it really does act like a cosmological constant. And so this is the semi-classical Einstein field equation, including dark energy, where we're just going to be agnostic about whatever quantum fields or quantum effects small lambda represents. All we need to care about is that whatever it is, we're coupling it to the space-time geometry by taking its expectation value and asserting by homogeneity and isotropy that that expectation value must be constant on natural space-like slices. So I hope that I've said enough to motivate the idea that the study of lambda, dark energy, and also inflation inter alia, because the inflaton field is supposed to be fundamentally a quantum field, even though it's actually almost never treated truly as a quantum field, but put that aside. It's supposed to be a quantum field. So the study of lambda, of inflation, and several other effects that we think may be important in cosmology, kind of a Hawking-like particle creation from the expansion of the universe, which contributes, we think, to the anisotropies in the CMB. These are all most naturally posed and studied in the framework of semi-classical gravity. And as we've already discussed, and as the name itself suggests, lambda is most naturally thought of as an energetic term, as an energetic quantity. But possibly, also as we'll see, and as Julius as was suggested by Julius's talk yesterday, lambda may also have some entropic-like character. And we will see that developed later in the lecture, how to make that idea more precise. So let's talk about energy and entropy in classical physics. Mm-hmm.
I just want to ask one technical thing
Sure.
about equation. Can you? Mm-hmm. So why we in the first row we only have lambda, and in the second row we have expected value of lambda?
So this lambda is just a constant. It's just a real number. Mm-hmm. And the idea is that if we think, as almost all models and accounts of dark energy propose, that it arises from some underlying quantum field or some underlying effect of a quantum field, then it really should be, this constant really should be written as the expectation value of the mass energy of this quantum field or the quantum fluctuations or whatever exactly they are. So I'm just rewriting this is just a real number. Remember, expectation values are real numbers.
Okay.
So I'm just rewriting this to make it explicit that we expect at bottom that lambda really should be a quantum in nature.
Okay, thank you.
So y'all know I love quoting people, and this is such a marvelous quote from Percy Bridgman, who you may know as the originator of so-called the operationalism view of certain facets of interpreting physical theory. So Bridgman says, the totality of situations covered by various aspects of the energy concept is too complex to be reproduced by any simple verbal device. I think we tend to think that of energy as a fairly simple quantity, especially in classical physics. But I think we do that because we actually forget about the real conceptual complexities that the idea of energy shows in classical physics, and that's what I hope to discuss. Because as a philosopher and a gadfly, I hope, in the Socratic tradition, one of my duties is to take a step back and remind us from time to time about some basic ideas that we tend to lose sight of because they're so deeply embedded, so fundamental to our conceptual frameworks in physics that it's rare that we stop and take a step back and really think about them. And so I'm going to begin with a few basic, almost trite, observations about energy and entropy in classical physics, and by this I mean non-relativistic, non-quantum, to set the stage for the discussion of the more advanced and abstract and abstruse matters once we hit semi-classical gravity. And in any event, one almost never goes wrong by beginning a talk with the invocation of the Fermi pleasure principle, which states, never underestimate the pleasure an audience gets from hearing what it already knows. So, what energy and entropy share in common in classical physics? They're both almost truly universal quantities. Every theory treating every kind of physical system in classical physics attributes, or at least can attribute, both energy and entropy to the systems they treat. Possibly, arguably, maybe the simple mechanics of rigid bodies, it's hard to attribute an entropy to that. And except, most interestingly, it doesn't seem to make sense to attribute an entropy to the Newtonian gravitational field. And this really is, this universality is striking, because if you think of any other physical quantity, viscosity, angular momentum, almost electric charge, it doesn't make sense to attribute those quantities to every kind of classical system. But energy and entropy do have this kind of almost universal character, which is quite striking. They both are fungible, and what that means is that no matter what, if I have two systems and each has energy of a particular kind, chemical energy, kinetic energy, what have you, in principle, it's always possible for the two systems to exchange energy. And in fact, for that energy to transform, for chemical energy to become gravitational potential energy, or whatever you like. And the same for entropy. If I have two entropic systems, it's always possible, in principle, to hook them up, no matter what form they take, fluids, dust, electromagnetic fields, elastic matter, elastic continuous matter. I can always, in principle, hook them up and have them exchange entropy, create an entropy flow from one to the other. Both are affine quantities. Neither has a natural zero point in classical physics. Each obeys a characteristic relation among all their possible forms. For energy, it's an equality, the conservation of energy. For entropy, it's an inequality, the second law. And interestingly, both of these relations have an intimate connection with time. Because one conception of energy is that energy is the generator of time translation time translations. And entropy, of course, in the second, and many people think that the asymmetry of the second law is intimately related to the direction of time. So energy seems related to the idea that we move through time, so to speak. And entropy seems related to the idea that our movement through time has a characteristic direction. And as I just intimated, there are at least, and I think we really do often tend to forget this, and I've not just philosophers, but physicists also. I gave a talk somewhat related to this to an audience at a conference on energy conditions and quantum field theory. And I was, in fact, not surprised at how many of the physicists came up to me afterwards and said, yeah, you know, I never think about that. You know, But there are really two entirely separate conceptions of energy in classical physics. One is, as I just remarked, the generator of time translations. That's most naturally associated with the Hamiltonian picture of classical physics. The Hamiltonian is a measure of the energy of the system, and it generates the dynamical evolution of the system by way of Hamilton's equations. But there's a second conception of energy, the capacity to do work. And that's most naturally represented in the Lagrangian framework. These two conceptions are a priori independent of each other in a very strong sense. And you can see this quite clearly, I think, by considering the facts that work depends only on spatial paths. Remember, work is defined as the integral of the force acting along a spatial path. There's no mention or notion of time in that definition whatsoever. And one can make precise the idea that it's independent of time by noting that the work one form in the Lagrangian framework is always transverse to accelerations. It's always transverse to the dynamical flow of the system. And the energy, remember, the Lagrangian is not the energy. Energy is a function of the Lagrangian. And in Lagrangian mechanics, the energy, including the work one form, does not generate the dynamical evolution. The Lagrangian generates the dynamical evolution. So energy in Lagrangian mechanics is really quite different from energy in Hamiltonian mechanics. And in fact, indeed, one cannot represent work. I have no idea how to represent the idea of work in Hamiltonian mechanics at all, much less dissipative systems where the notion of work really becomes really very important. The two conceptions of energy are brought into contact with each other by way of the conservation principle. But as they realized in the 19th century, in order to really make conservation of energy work, they had to introduce a third term, heat. And heat, it turns out, is in fact a third completely independent notion of energy in classical physics. And once you introduce heat, heat is neither a generator of time translations, and neither is it a measure of the capacity of a system to do work. But once you introduce heat, you inevitably, almost against your will, you just can't help it. You are led to introduce entropy from energetic considerations about the transformability of heat into work. Limitations on the transformability of heat into work and vice versa. So there really are three conceptions of energy. They're united by the conservation principle and by the second law, most explicitly in the form of the Kelvin postulate. So recall the Kelvin postulate says it is impossible. There is no physical process whose sole result is that heat is extracted from a source at constant temperature throughout and transformed entirely into work. So that is a very strong relation between heat and work, at least, that is independent of the conservation principle, but must be accounted for in trying to understand what energy is, what role it plays in classical physics. And tantalizingly also, the characterization of equilibrium as the maximizer of entropy and the minimizer of free energy is another relationship between energy and entropy that is very suggestive that these two quantities have some close relation in classical physics. Now, I can never resist quoting Maxwell because Maxwell is one of my heroes. I personally think that Maxwell was the most philosophically sophisticated and deep physicist who ever lived, even more so than Newton or Einstein. I actually put Maxwell first, Newton second, and maybe Einstein third or fourth. But he has such a marvelously rich and clear philosophical mind. So in his beautiful book, The Theory of Heat, Maxwell remarks, "Now when the appearance of one thing is strictly connected with the appearance of another, so that the amount which exists of the one thing depends on and can be calculated from the amount of the other which has disappeared, we conclude that the one has been formed at the expense of the other, and that they are both forms of the same thing." He is giving us, if you like, the metaphysical foundation for the idea that even though entropy and energy come in different forms, these mathematical relations among them, several of which I've gestured at and articulated, give us, again, if you like, the metaphysical grounding for the assertion that all these prima facie different forms of quantities are at bottom really the same thing. All forms of energy really are one thing, even though they have different characteristics. All forms of entropy are really one thing, even though they have different characteristics. And I mean, note how careful Maxwell's formulation is, because it applies both to energy, conservation and equality, and to entropy, the second law and inequality. So, nonetheless, I've tried to articulate ways in which energy and entropy in classical physics are very closely related, and they are closely related in really important ways that are still to me somewhat mysterious and obscure. I don't fully understand the relation between them even in this most simple of settings. But there are still nonetheless very clear conceptual and physical differences between the two. Most fundamentally, they are not jointly fungible. I can't turn entropy into energy and vice versa. There is no such thing as an entropometer. There's no device, there's no instrument I can build that directly measures entropy, that, in the sense of measurement that Vera was talking about, as an instrument that directly couples to the physical system under study by way of the quantity entropy. But there are ergometers. I can measure energy directly. I can build an instrument that will interact with the system at interest insofar as its interaction with the system is mediated by the energy content of the two systems. Entropy is not like that. And part of the reason for that is that entropy, in a funny way, is a modal quantity. Entropy is not, in many ways, entropy is not a property of the instantaneous state of a system. So in Boltzmannian statistical mechanics, the Boltzmann entropy is the measure of the phase volume of the macro state. But the macro state, remember, is consistent with an infinite number of microstates, only one of which, presumably, is actually instantiated. We have a box of gas. The atoms in the gas at a given moment of time each have a distinct position and velocity. That's the microstate. The pressure and the temperature and the volume are the macrostate. But that same pressure, temperature, and volume are consistent with the gas being in an infinite number of different distributions of positions and velocities. The entropy is a measure of the size of all the possible microstates that's consistent with the macrostate. But that's if you like, a modal counterfactual property. How many ways could the gas be and still be consistent with the macrostate? So entropy is a really, really weird quantity. Energy conservation must be postulated. You can't derive it. But it plays an essential role in the derivation of many important general results. The principle of entropy non-decrease, which is often called the second law, and in fact I've been calling it the second law a few times here, it's really not the second law. The second law really is the Kelvin postulate or the Clausius postulate, which one can argue are physically equivalent. That the principle of entropy non-decrease can be derived, unlike energy conservation, but weirdly, to me, it plays no essential role in the derivation of any important general result. I don't know of any important general result in classical physics that one derives from entropy non-decrease. Entropy non-decrease is incredibly important in practical applications of thermodynamics. It's used all over the place in organic and inorganic chemistry to characterize possible routes of molecular interactions, to rule out certain kinds of interactions as entropically not possible. Entropy plays, the principle of entropy non-decrease plays an incredibly important role in placing constraints on how kind of specific kinds of systems and specific kinds of states can transform into new states in the future. But I don't know of any like really important general theorem that entropy non-decrease plays a role in. I find that very weird. And as I just remarked, entropy constrains the possible future the future transformations of a system much more severely than energy conservation does. In fact, another quote. The great thermodynamical physicist Richard Emden. So this article, by the way, it's a 2-page article. I strongly urge everyone to read it. It's just beautiful. It's so insightful. So Emden says, as a student, I read with advantage a small book by F. Wald entitled The Mistress of the World and Her Shadow. By the way, I was just curious whether this F. Wald was related to Bob Wald, you know, the great general relativist quantum field theorist today. And Bob said no, he has, as far as he knows, there's no connection. But anyway, he read with advantage a small book by F. Wald entitled The Mistress of the World and Her Shadow. These meant energy, the mistress, entropy, the shadow. In the course of advancing knowledge, the two seem to me to have exchanged places. In the huge manufactory of natural processes, the principle of entropy, by which he means entropy non-decrease, occupies the position of manager, for it dictates the manner and method of the whole business, whilst the principle of energy, merely the conservation principle, merely does the bookkeeping, balancing credits and debits. So let's now look how energy and entropy, the concepts of them and their ideas and the roles they play in the physical theory become transformed when we move to general relativity. So many, but not all, of the properties of energy carry over from classical physics, and in fact are even deepened and become more subtle in general relativity for many different aspects of energy that were kind of independent in classical physics, become united in a single quantity, the stress energy. So the stress energy tensor contains terms that are contributions of ordinary shear and stress, which are kind of work, and momentum flux, which is associated with work, and the simple mass energy density, which is really like the Hamiltonian. So there's not a complete unification of the two conceptions of energy. Energy is the capacity to do work, energy is the generator of time translations. But they become much more intimately related. They are, in a sense, unified insofar as one can really make sense of them at all in general relativity. They become unified into a single energetic quantity, the stress energy tensor. We still have universality. It is, in fact, it is almost definitive of what we mean by matter in general relativity, that it possesses a stress energy tensor. And every single form of matter couples with gravity, with the space-time geometry, by way of the stress energy tensor. So there's the fundamental energetic concept in general relativity still has a kind of universality. We must attribute it to every kind of matter field we treat, and that attribution, the fact that matter possesses all kinds of matter possess this energetic kind of quantity, is what gives gravity its universal character. Gravity, you know, as per the principle of equivalence, affects all matter in the same way. It is unlike every other known force of nature in that regard. Not everything has an electric charge, so not everything is affected by electromagnetism. Not everything has a weak nuclear charge, so not everything is affected by the weak nuclear force. Not everything has a strong nuclear charge, not everything is affected by the strong nuclear force. Everything has inertial mass, everything has stress energy. Gravity is universal. And that is part and parcel of the universality of stress energy. It's still fungible. Every form of stress energy can be transformed in principle into every other kind. If I have a Navier-Stokes fluid and I have an electromagnetic field, they each have their own stress energy. In principle, I can hook them up together and exchange. I can engineer an exchange of stress energy, say from the electromagnetic field to the Navier-Stokes fluid. There's still a conservation principle, but it becomes radical. This really becomes a radical transformation in general relativity. The conservation principle is, in a sense, only hyperlocal. The covariant divergence of the stress energy tensor is 0. There is, in general, no associated integral conservation laws. But I sadly don't have time to talk about it, but the whole idea of energy as a unified concept in classical physics and the conservation principle depends not only on the differential form of the conservation principle, but really depends very strongly on the fact that we can transform the differential principle into an integrated integral principle over finite regions of space and time. In general, we can't do that. So you may recall when I was introducing, I think the lecture on the first day, when I was introducing the idea of a cosmological model and I began to talk about FLRW spacetimes, one of the features of FLRW spacetimes I mentioned is that there's no strict energy conservation. One always has this kind of hyperlocal conservation. It holds at a single spacetime point, so to speak. But in general, you can't integrate it up over finite spacetime regions. And strikingly, we now actually have a natural 0 point. Energy is no longer an affine quantity. Stress energy tensor equals 0 is unambiguous. You can't, in Hamiltonian mechanics, I can always add a constant to the Hamiltonian without changing anything. I'm just rescaling. I'm just resetting what I'm calling 0 energy. I can't add a constant to the stress energy tensor. It really does have a natural 0 point. And energy conditions, which I gestured at briefly in the discussion of FLRW models, now make their first appearance in physics. So for instance, the weak energy condition says that if I take any time-like vector whatsoever at a point, and I contract it with the Einstein tensor, that is always greater than or equal to 0. And the physical interpretation of this, by setting the Einstein tensor equal to the stress energy tensor, is that everyone sees positive mass energy. So these energy conditions place constraints on measures of curvature, like in this case on the Einstein tensor, but it can also place constraints on the Ricci tensor or on the Weyl tensor or on the Bell-Robinson tensor, on other measures of curvature. And these constraints on the measure of curvature, as I just intimated, are given physical interpretation by way of the stress energy tensor in the Einstein field equation. There's a sense in which the Einstein field equation has almost no physical content on its own. I tend to think of the Einstein field equation very much in the same way as I think of Newton's second law. Newton's second law, by itself, is applicable to every kind of system Newtonian mechanics treats. If you like, it's kind of like a logically second-order formula. The f on the left-hand side is a second-order variable. I can fill it in with any kind of force for any kind of system I like. It can be pressure from a gas, or sound waves in an elastic continuous medium, or percussion impact pressure, from two particles hitting each other. And the same for acceleration. The acceleration term on the right-hand side can represent any kind of change of something like spatial configuration with position, twice over. It can be, the change in the moment of inertia of a quasi-rigid body as it's rotating, or it can be the measure of the acceleration of the fluid, of the velocity flow in a fluid. Newton's second law by itself doesn't tell you what kind of system you're dealing with. It doesn't tell you, it's like a schema, it's like a placeholder. The Einstein field equation is very much the same way. It,
I heard that actually the initial, if I can say, shape of this law was the change of momentum with change of time, and not the product of mass and acceleration. Just that. I don't know, does it has some implication, but yeah.
no, so as a historical fact, that's a really interesting historical fact. If you read the Principia, Newton's Principia, which again I very strongly urge you all to do, it's probably the most beautiful, amazing book ever written. Newton's own formulation of the second law in the Principia is not F equals ma. That's actually due to Euler. Newton's law, Newton's own formulation of the second law is given today in what we call impulse, the integral of momentum change. The force equals the integral of momentum change. There actually was there's actually a very good reason for that. Newton knew full well, Newton developed the calculus, Newton knew full well that in a certain weak restricted sense, the integral form that he stated was, under restricted conditions, equivalent to the derivative form that Euler made canonical. But Newton preferred the integral form because it allowed him to treat particle collisions. Because in inelastic particle collisions, the velocities change discontinuously, and that you can't use derivatives to model that. But you can use the integral of momentum change to model that. So Newton had a very good reason to do that. But I don't think it changes the fundamental point that I was making. But it is a...
And also I think it's better refers to the first law of Newton.
What does? I'm sorry.
Because of momentum, he tells that...
I see what you're saying.
You know what I'm saying. I think it more refers to first. There are like a better connection between first and second law if we define second law as a change of momentum or impulse through time.
Oh, that's an interesting point. I'll have to think about that. That hadn't occurred to me. So that was a very rather long-winded justification of the claim that on its own the Einstein field equation has almost no physical content. And in fact, to get any traction, to prove all of the deep, important theorems that we use in general relativity to characterize black holes, to characterize singularities, to characterize cosmological evolution, you always have to impose an energy condition. You can prove almost nothing if all you have is the Einstein field equation. Just like if all I know is Newton's second law, you can prove almost nothing from that. You have to impose constraints on the kinds of systems that you want to treat in order to get some traction and begin to prove really substantive, general, deep results. And in almost every single case, what the imposition of the energy condition does is it guarantees focusing of geodesics. So you recall again from the lecture on the first day, I wrote down the Ray-Chuduri equation, and which governs the relative behavior of neighboring geodesics, and remarked that some people refer to it as the fundamental law of gravitational attraction in general relativity, because that's more or less what it does. The fact that energy is positive, as captured, say, by the weak energy condition, means, when you plug this into the Ray-Chuduri equation, it means that, other things being equal, nearby geodesics tend to accelerate towards each other, rather than accelerate away from each other. That's just to say, positive mass energy leads to what we normally think of as gravitational attraction. But this focusing of geodesics, the fact that freely falling bodies, bodies, quote unquote, under the influence of no force except gravitation, the fact that freely falling bodies accelerate towards each other is guaranteed by the energy conditions, and it really is the most characteristic role of energy in general relativity. It's what is used in proving all of these deep theorems about black holes and cosmological evolution and on and on. It's also most characteristic of the following is also most characteristic of energy conditions in GR, and this is also somewhat puzzling. In classical GR, as in almost every theory I know of, one has a great deal of freedom in what one takes as a primitive, as a fundamental assumption, and what one derives as a derivative principle. So as an example, one can take the covariant conservation of stress energy, the covariant divergence of the stress energy tensor equals 0. One can assume that and derive the geodesic principle from it. Freely falling test particles traverse time like geodesics. But one can actually do the opposite also. One can assume the geodesic principle and derive the conservation of stress energy. You have a great deal of freedom in what you assume and what you derive. That is not true for energy conditions. You cannot derive an energy condition in classical GR from some other fundamental principle. In classical GR, they are always stipulated as just fundamental, brute properties of matter fields. So one might, as a very vague conceptual speculation, one might then imagine, well, if you can't derive them, but you are forced to assume them to make any progress in GR at all, maybe they're like kind of reaching down and getting a hold of something very, very deep in the physics of space-time geometry and matter and interaction. Now, that's a very vague speculation. I don't know how to make it more precise, but it feels like there's something right there, but I can't tell you exactly what it is. There are entropy conditions in classical GR. They're much more subtle and complex. The most important one is the so-called Busso entropy bound. And you can derive this entropy condition. So the Busso bound basically states that the flow of that under certain restricted conditions, which are among other important applications relevant to black hole physics, a certain measure of entropy is always positive. Entropy doesn't decrease. And in fact, it gives you a bound on how much entropy there can be for an associated amount of energy. You can derive this entropy bound, this Busso bound, from an energy condition. This is the so-called dominant energy condition. Busso actually didn't derive his entropy bound from the dominant energy condition. He motivated it, gave a heuristic argument for it. But very, very quickly afterwards, Flanagan, Walden, Morolf actually gave a rigorous proof of the Busso bound using the null energy condition. So again, the relations between energy and entropy in classical GR they're kind of neighborly. They talk to each other. They impose some constraints on each other, but they're still not really very intimate. For one thing, the relationship between energy conditions and entropy conditions is one way only. I can use energy conditions to derive entropy bounds and entropy conditions, but I can't go the other way. I can't use constraints on entropy to derive an energy condition. There's no explicit unification of different types of entropy in something like a generalized second law, as there is for energy. We don't have a single unified quantity in general relativity that unifies all different forms of energy in the way that the stress energy tensor seems to for energy. Energy and entropy are not jointly fungible if you accept Wald's way, the orthodoxy, that there is no consistent thermodynamical theory for purely classical black holes. There's still no entropometer. Even if you think that classical black holes have an entropy, can't measure it. And the relation of both stress energy and entropy to equilibrium, which in general relativity, equilibrium, the only really natural way to think about equilibrium is the existence of a time-like killing field, a flow in the space-time under which the metric remains constant. So it's like a time-like symmetry. The space-time, in an important sense, isn't changing over time. That's pretty much what equilibrium has to mean in general relativity. Mm-hmm.
Because you said that there is still no entropometer, does it mean that maybe we actually can construct, so there is a possibility that we can construct such a device, or because it's still no entropometer?
Well, in fact, when we get to semi-classical gravity, I won't tell you the answer. Okay. Just I'll hold you in suspense. Okay. Keep you on the edge of your seat. But things get more interesting when we move into semi-classical gravity. So the relation of both stress energy and entropy to the notion of equilibrium that general relativity makes available to us is obscure at best. So there's a sense in which in general relativity, we actually seem to have lost some of the connections between energy and entropy that we had in classical physics. And in any event, already energy here goes beyond the role it plays in non-relativistic physics, because now not energy conservation, but these energy conditions, these inequalities, which, by the way, should be reminiscent of something like a second law. Because, the thermodynamical second law is an inequality, not an equality. Energy conditions begin, to paraphrase Emden's marvelous remark, in the huge manufactory of natural processes, stress energy begins to occupy the position of, if not manager, maybe assistant manager, for they constrain the manner and method of much of the whole business. So there's a certain sense in classical GR in which the relationship between energy and entropy becomes less intimate. We've lost the connection to them through, by way of equilibrium. But in some ways they become more similar. Stress energy starts to play a very similar role to the role that entropy played in classical physics by way of the energy conditions, these inequalities. So I was talking with Ravelli a couple of months ago about a lot of this stuff. And he made this wonderful remark. He said, entropy and thermodynamics in general is not yet understood by anybody, even in classical gravity. What is well understood since Tolman, a great cosmologist in the 1930s, is the thermodynamics of matter fields on a given geometry, which is to say, disregarding dissipation into gravitational degrees of freedom. But dissipation into gravitational degrees of freedom has no reason not to occur, which in the black hole case is the classical analog of some observations I made about gravity getting entangled with Hawking radiation. So the classical thermodynamics of the gravitational field is a topic for which we do not have a science at all yet. And I completely agree. Trying to understand how geometry and gravity may or may not have an associated entropy in classical general relativity is at best poorly understood, at worst not understood in the slightest. So in Ted Jacobson's really remarkable paper, 1995 paper, The Thermodynamics of Spacetime and the Einstein Equation of State, in the very, I think if I recall correctly, this is the very first paragraph of the paper. He asks this very plaintive question. How did classical general relativity know that the horizon area would turn out to be a form of entropy and that surface gravity is a temperature? Because in black hole thermodynamics, the entropy of the black hole is proportional to its area, one quarter of the area. And the temperature of the black hole is proportional to its surface gravity. It's the surface gravity divided by 2 pi. And black holes, in the context of classical general relativity, one can derive the so-called 4 laws of black hole mechanics, which govern the behavior of classical black holes and which are in perfect formal analogy with seeming the 4 laws of ordinary thermodynamics. So the 0th law, system in equilibrium has constant temperature throughout. For thermodynamics or black holes, a stationary black hole has constant surface gravity. The 1st law, energy conservation, is identical. There's a principle of energy conservation for a statement of energy conservation for black holes, that the change in energy is proportional to the surface gravity times the change in area plus rotational work terms. If you take surface gravity as temperature and area as entropy, it's identical to the Clausius relation in ordinary thermodynamics. The 2nd law, entropy doesn't decrease, is captured by the Hawking area theorem. The area of a black hole doesn't decrease under any allowed physical process. The 3rd law, it's impossible for thermodynamics. It's impossible for to bring any physical system to absolute 0 by any allowed physical process. For black holes, It's impossible to reduce the surface gravity of a black hole to zero by any physical process. So in classical general relativity, without taking quantum effects into account at all, on its own, seems to come tantalizingly close to saying that black holes are thermodynamical objects. They obey the exact formal analogs of the four laws of thermodynamics, just in the purely classical regime. And then, of course, it was Hawking's discovery in 1974 that black holes seem to emit perfectly thermalized radiation, a Planck spectrum of radiation with the power spectrum characteristic of a thermodynamical body at temperature equal to surface gravity divided by 2 pi, that made people believe that black holes really are thermodynamical systems. Because every thermodynamical system we know of gives off black body radiation. And the kind of physical temperature of any thermodynamical system, as measured by the variance in the kinetic energy of the molecules, is equal to the temperature as characterized by the Planck energy spectrum in the emitted black body thermal radiation. And so Hawking showed that black holes behave in exactly the same way. And that's what made people really believe that black holes were thermodynamical objects, because the four laws of black hole mechanics were actually developed in a paper. They're given their final form in a paper by Bardian, Carter, and Hawking in 1973. But they say explicitly in that paper, this is just a formal analogy. It's an interesting curiosity. It doesn't mean black holes have real thermodynamical properties, primarily because they don't emit black body radiation. But somehow or other, even if you accept that in classical general relativity, even though black holes formally obey the same laws as the laws of thermodynamics, but they aren't truly thermodynamical objects until you take quantum effects into account. Nonetheless, as Ted very plaintively and I think really rightly asks, I think Ted is putting his finger on an incredibly important point. Somehow or other, this idea that the area of a black hole is its entropy and the surface gravity is its temperature is already there in classical general relativity. And then taking quantum fields into account and the behavior of quantum fields kind of makes us take the analogy more as not simply a mathematical formal accident, but as true physical equivalence. In the context of quantum field theory on curved space-time, when you use quantum fields rather than classical matter and you couple them to black holes, then the laws of black hole mechanics just become the ordinary laws of thermodynamics extended so as to cover this new class of physical systems. In exactly the same way as at the end of the 19th century, they had thermodynamics in the 19th century was primarily the study of ordinary material systems like solids and liquids and gases. But by the end of the 19th century, they had realized that in order to save the second law of thermodynamics, they had to attribute an entropy to the electromagnetic field, to black body radiation. And they had to attribute a temperature to the electromagnetic field, to black body radiation. So the scope of thermodynamic laws at the end of the 19th century got extended from solid liquids and gases to electromagnetic radiation. And now it seems as though a similar thing is happening. We take the laws of thermodynamics, the laws that apply to solids, liquids, and gases, and electromagnetic radiation, and we now extend them again to encompass a new type of physical system, black holes. But why did classical general relativity know this? Why is the seeming signature of the thermodynamical character of black holes already encoded in classical general relativity? Well, the most basic reason for thinking that there is an intimate relation between energy and entropy in semi-classical gravity comes first and foremost from, in fact, black hole thermodynamics. So special relativity tells us that energy and mass are equivalent in a strong physical sense. General relativity tells us, the first law of black hole mechanics, what I gestured at a few minutes ago, that in any physical process, under some mild constraints, when a black hole is interacting, with some matter, if I toss in a bit of matter to the black hole, the change in the mass of the black hole is equal to 1 over 8 pi times the surface gravity times the change in the area. And if you remember your basic thermodynamics, this is exactly the Clausius relation. The change in energy of a thermodynamical system near equilibrium is just its temperature times its change in entropy. This is the Clausius heat term. So again, taking surface gravity to be temperature, area to be entropy, mass just is energy, we have identical statements. And now semi-classical gravity tells us, when we take, when we take the Hawking effect into account, that in fact that the entropy, that this area really is an entropy, the so-called Bekenstein entropy, and it's proportional to the mass squared of the black hole. So energy can now be directly transformed into entropy. Yes, please. Oh, wait, we need to get you the microphone.
It's about the topic. I just got lost for a second. And what happened with the work energy component in semi-classical gravity?
So, what I wrote down is for a Schwarzschild black hole, for a non-spinning black hole. If you're studying a Kerr black hole, say a black hole that's rotating, then in fact you do have to add an extra term here, which is that. So omega is the angular velocity of the black hole, and J is the angular momentum of the black hole. But this is the angular work term of a classical system. The work done by a rotating system is its velocity times its change in angular momentum. So the first law for spinning black holes is not only has this heat term, it also has this rotational work term. And then if you extend it and you consider Kerr-Newman black holes that also have electric charge, you'll get a further term here that if there's a change in the charge of the black hole, the change in the energy just is the electric potential times the change in charge. But again, that's identical to classical electromagnetic systems. The amount of work done just is the potential times the change in charge. Mm-hmm. There's another question back there.
Maybe this takes us too far away from this, and so then please tell me and I'll shut up. But like when
Shut up. Oh wait. Sorry.
when we do have like a version of the Hawking formula for evaporation, including charge and angular momentum, like can I expect that like those two will evaporate before the rest of the mass evaporates, sort of?
So
will it converge to Schwarzschild before finally evaporating, or will it always be like Kerr-Newman-like?
So let me see if I understand. So we're considering let's say a Kerr-Newman black hole. It has it's both spinning and it has electric charge.
Yeah.
And we're letting Hawking radiation go away, so the black hole is losing energy, so it's evaporating, it's shrinking. And your question is.
Well, I guess J and Q should also sort of like, disappear or evaporate throughout the process.
Yeah, eventually,
will they go to zero before n goes to zero, or?
Or
will they be kind of like coupled and?
Yeah, so it entirely depends on the kind of quantum field that you're considering coupling to the black hole. So if you're coupling, say, a scalar field without charge, then this won't change. It will eventually vanish because all the energy is vanishing. But during the radiation process, if it's giving off electrically neutral scalar field radiation, this will quote unquote vanish at the very end. It'll have the same electric charge all the way to the very end, and then
Wow,
when the black hole
okay.
disappears, it'll just go to
So
just
it
continue
will
to go to zero.
extremize actually before.
Yeah.
Okay.
That's right.
I'll shut up now.
No,
but I will want to talk to you about that.
It's a really interesting question. But yeah, short answer, it entirely depends on the nature of the quantum field you're coupling to the black hole and how you're allowing it to radiate. So it now turns out that energy can be directly transformed into entropy. If I throw a bit of stuff with mass energy into the black hole, its area increases, the entropy increases. I've transformed the mass energy into entropy. And vice versa, I can transform entropy into energy because the mechanism of Hawking radiation is that the energy of the black hole, the mass energy of the black hole is shrinking as the Hawking radiation is being given off. The area of the black hole is shrinking, the entropy of the black hole is shrinking, the entropy is being transformed into the energy of the Hawking radiation. They both now have, both energy and entropy, both now have a natural zero point, and it's in fact the same state of space-time and quantum fields. It's the Schwarzschild solution with mass equals zero. We now have a connection between energy and entropy for characterizing equilibrium. There are not rigorous, but there are heuristic and I find very compelling arguments that stationary black holes minimize free energy and maximize entropy. And we now have an entropometer, weirdly enough, because we can measure the area of the event horizon directly. Entropy it seems like for a black hole, entropy is no longer a modal quantity. There are some real subtleties that I'm glossing over here. But at least in the framework of semi-classical gravity, where we're not allowing ourselves to imagine that the gravitational degree that there are underlying micro gravitational degrees of freedom, maybe quantum gravitational degrees of freedom. In the framework of semi-classical gravity, there are no gravitational micro degrees of freedom, so the area just is the entropy, and we can directly measure it. And in this case, the entropometer is also an ergometer, because if I know the area, I also know the mass. I know the energy. The area is both the entropy and the energy are functions of the same quantity, the mass. But in fact, the relations, including equalities between entropy and energy, even beyond those just stated, become a really promiscuous, libertine, orgiastic debauch. So it's Sodom and Gomorrah during the fun times, before everything went to hell. So, and lambda, it turns out, dark energy, no matter how one wants to think of it, seems to itself manifest this much more intimate connection between energy and entropy. So the straightforward interpretation of lambda is it's an energy. We call it dark energy. But from Julius's talk yesterday, we already had some intimation that lambda acts like an entropy when the energy of ordinary matter becomes so diffuse and so the energy density becomes so low that lambda dominates. The universe begins to act like a system in perfect thermal equilibrium. You can't retrodict. But there's even more direct evidence that lambda really behaves like an entropy. Ted Jacobson and Magnus Visser have this really beautiful argument that if you have a generic space-time and a causal diamond in a space-time, so let this white box represent some generic space-time. I love white boxes I love black squares on chalkboards and whiteboards. They're just infinite possibility. It can be any space-time I want. Representational capacities are endless. So a causal diamond is, I take two space-time points, one of which is to the causal future of the other. I draw the forward null cone of this one, and I draw the past null cone of that one. Then that's the so-called causal diamond. That's a so-called causal diamond. So it turns out that if you're in any space-time whatsoever, if you make the causal diamond small enough so that curvature is effective, so that you're almost ignoring all the curvature. It's very much like the situation on the surface of the Earth. We know the Earth is really a curved surface. It's a sphere, but the curvature is so large that when we're walking around in ordinary life, we effectively treat it as flat. We can ignore the Earth's curvature. So you do something similar. You give me almost any old space-time, and I can find and you give me any region in that space-time, any two very, very near. I can find 2 points that are very near to each other, so that the causal diamond that they define is almost flat. But you can always arrange it so that it actually looks like de Sitter space-time, which is the vacuum space, the unique maximally symmetric vacuum space-time with a positive cosmological constant, which, recall from Julius's talk, is exactly what we expect by the cosmic no-hair theorems for certain cosmological models to asymptote to end up with.
Even for Planck lengths?
No, not for Planck length. It has to be bigger than Planck length, but smaller than ordinary matter scales. But you have a lot. You have a lot of room to work with there because the effective diameter of a proton is what, like 10 to the minus 14 centimeters, and Planck length is 10 to the minus 32 centimeters. So you have like 18 orders of magnitude there to work with. So Ted and Manus have this really beautiful argument that these generic causal diamonds with de Sitter geometry with positive lambda maximize gravitational entanglement entropy. So it seems like positive lambda, dark energy, is not just in cosmology, but generically for gravitational fields, quite generally, acts as an entropy maximizer.
Erik, just a clarification. What do you mean with gravitational entanglement entropy?
It's a good question. So let's say that we have this causal diamond, and there's some quantum field in the background. So do you know what the von Neumann entropy is in ordinary quantum theory? So what you do is you treat, say, you take this space-like surface that goes through your causal diamond, and you can attribute, an ordinary entropy to the matter distribution of the quantum field on this space-like slice. And I can now define, I can now compute the von Neumann entropy outside the causal diamond by tracing out the degrees of freedom of the quantum field inside the causal diamond. That's the definition of the von Neumann entropy. For various reasons, people in this field, people refer to this as the entanglement entropy. And so the gravitational entanglement entropy, or von Neumann entropy, if you like, is what you get precisely when you have a region of space-time that's bounded by null hypersurfaces. So these are all null surfaces, and you trace out the matter, the quantum degrees of freedom outside the causal diamond. Then that defines the entanglement. That is the definition of the entanglement entropy inside the causal diamond. And the reason it's called the gravitational entanglement entropy is because you end up getting contributions from the area of these null hypersurfaces, just like the area of the event horizon of a black hole. We need to attribute an entropy to that area, and the entanglement entropy, the von Neumann entropy of the quantum field that you get from tracing out everything outside the causal diamond. So one of the most natural ways to think of gravitational energy in GR, which is really weirdly hasn't been explored a lot by physicists, is geodesic deviation, focusing of geodesics. Because if I want to extract energy from a gravitational field, there has to be some geodesic deviation. I need to have relative acceleration. If I want to, construct a pulley with a mass on one end and have gravity pull the mass down, And on the other end of the rope, I have, say, there's some sandpaper and a rock, and as the mass on one end of the pulley goes down, the rough rock goes up and scrapes across the sandpaper and generates friction heat. That works. I'm extracting energy from the gravitational field only because there's a gradient. There's a gravity gradient. There has to be geodesic deviation for me to extract energy from the gravitational field. If there's no gravitational gradient, that mass isn't going to move, and I can't extract energy.
So geodesic paths are equilibrium paths?
I'm sorry?
Geodesic paths
Um,
of curves are equilibrium?
So geodesic paths are the paths that freely falling bodies traverse. So when quote unquote they experience no force except for gravity. So for instance, right now I am not in fact I'm not on a geodesic because the floor is holding me up. The floor is exerting a pressure to keep me. We normally think of, when we're standing here, we normally think of ourselves as at rest. But in fact, I'm accelerating right now because the floor is exerting a force to hold me in place. It's only when I do this that I'm actually traveling a geodesic. When I'm going up and I'm going back down, I'm on a geodesic. When I'm standing, because I'm then, quote unquote, experiencing no force except for gravity. But gravity wants to pull me towards the center of the Earth. The floor is stopping me. So right now, no geodesic. So again, you can extract energy from a gravitational field when and only when there is geodesic deviation. When and only when nearby freely falling bodies are accelerating towards each other or accelerating away from each other. Otherwise, you can't extract energy from a gravitational field. As we'll see in semi-classical gravity, well, before I say that, I'll say one more thing. Recall when we were discussing energy conditions in general relativity, in classical general relativity, I remarked that the most characteristic role that energy conditions play in classical general relativity is guaranteeing geodesic focusing, is in guaranteeing geodesic deviation. And in particular, if there's positive energy, geodesics accelerate towards each other. We'll see now that entropy becomes directly associated with, enforces geodesic deviation, focusing, not just positive energy. So entropy conditions, bounds and relations on possible entropy content of various kinds of gravitational and material systems begin to play the role that energy conditions play in classical GR by guaranteeing geodesic focusing. So energy conditions, so you can show straightforwardly that certain kinds of entropy conditions imply geodesic focusing. You can use the generalized second law. So the generalized second law is the ordinary second law of thermodynamics extended so as to include contributions from so-called gravitational entropy, say from black hole entropy. So the statement is no longer the entropy of ordinary matter does not decrease under any allowed physical process, but rather the gravitational entropy plus the entropy of ordinary matter does not decrease under any allowed physical process. It turns out you can use the generalized second law to prove singularity theorems, to rule out traversable wormholes, to rule out negative mass, to rule out other forms of quote-unquote faster than light travel. You can use it to restart inflation. You can use it to rule out restarting inflation. You can use it to rule out the existence of closed time-like curves. So almost everything that you use energy conditions for in classical GR, it turns out you can use the generalized second law, which is a relationship on gravitational entropy and material energy, to prove the same results. The Busso bound, which I mentioned earlier, now in the quantum regime, you can use to prove a singularity theorem. The quantum version of the Penrose inequality, the Penrose inequality is a bound that relates the possible maximal size of event horizons with the amount of mass energy available. So a quantum Penrose inequality, whoops. Wait, where was I? There we are. you can use a quantum version of the Penrose inequality based on generalized gravitational energy to place constraints on the ADM mass. You get what is called quantum focusing, which is a certain kind of focusing, which is a certain condition on gravitational energy that, again, imposes geodesics to prove singularity theorems, the generalized second law, boundary causality. You can use quantum focusing, in fact, to imply a cosmological version, to derive a cosmological version of the generalized second law. So almost everything that classical energy conditions did in classical GR, you can now do using entropy bounds, entropy conditions. So entropy begins, it looks like, to play very much the role of energy conditions. And interestingly enough, remember I remarked that the principle of entropy non-decrease in classical thermodynamics is kind of conceptually sterile. You can't use it to prove important general results. But now entropy becomes conceptually really quite interesting. It can be used to prove very deep general results about the generic behavior and structure of gravitational systems interacting with quantum fields. And also, one has now for the first time derivations of energy conditions. So remember I remarked that in classical GR, you can't derive an energy condition. They just seem to be absolutely basic and brute. But in semi-classical gravity, you actually can derive energy conditions based on entropy conditions. You can derive the achronal average null energy condition from the generalized second law. You can derive the average null energy condition from the quantum null energy condition, which is really, it's called the quantum null energy condition, but it's really an entropy condition. You can prove the null energy condition from the generalized second law. You can derive the quantum null energy condition itself from entropy conditions, and you can derive the null energy condition. You can interpret the null energy condition as an entropy creation term for dynamical black holes. In the interest of time, I will not go through the full explanation of the quantum null energy condition. It's a little complicated. But for our purposes, the important bit is that the heart of the quantum null energy condition is that the expectation value of the null term of the stress energy tensor, so the mass energy density term of the quantum stress energy tensor for quantum fields, is strictly bounded from below by I'm getting a little tired. I'm losing words. Variations. That's the word. By the second variation of a generalized entropy. So again, we now have interchangeable bounds. Energy and entropy are placed constraints on each other for what possible values they can have. Again, I won't go through the details of explaining the quantum null energy condition. We just don't have time. But even more strikingly, one gets not only inequalities between energy and entropy, one actually gets equalities. So you can use the same kind of geometrical arguments that are used to discuss the quantum null energy condition to show that second variations of the von Neumann entropy, that's what this is the second variation of the von Neumann entropy effectively, not only places a lower bound on the stress energy, on the mass energy component of the stress energy tensor, the quantum stress energy tensor, it actually completely determines it. It determines the full stress energy tensor expectation value as an equality. So you actually get a true equality between energy and entropy. And you can also show that one of these quasi-local energetic quantities, the Bartnik-Bray inner mass, exactly equals the irreducible mass corresponding to the outer entropy for null surfaces as defined by Netta, Engelhardt, and Aaron Wall. So you have it, and you begin to see that that energy and entropy begin to determine each other in exactly the way one would expect from quantities that are rather different facets of the same thing as opposed to being entirely different things. And perhaps most strikingly along these lines, I unfortunately, again, I don't have time to go through the argument, it's a little technical, but Manu Spitzer has this really lovely argument that shows that, in fact, not only does the generalized entropy, so generalized entropy is the gravitational entropy plus the entropy of ordinary matter, that not only does the generalized entropy obey an inequality, the generalized second law, but it actually obeys a first law also, a conservation equation, an equality. So generalized entropy really is behaving exactly like energy and playing exactly the same role as energy. And in fact, it does, and the way you derive this is by calculating expectation values of the stress energy tensor. So recall Maxwell's quote, Maxwell's metaphysical motivation for identifying different forms of energy and different forms of entropy. Now, when the appearance of one thing is strictly connected with the appearance of another, so that the amount which exists of the one thing depends on and can be calculated from the amount of the other, which has disappeared, we conclude that the one has been formed at the expense of the other and that they are both forms of the same thing. So the exact same kinds of principle that led us to think of prima facie different forms of energy as being really simply different facets of the same underlying unified quantity, I think push us, not definitively, not ineluctably, but very strongly suggest, to my mind, that energy and entropy, once we get into semi-classical gravity, may in fact be different aspects or different forms of the same underlying entity. Just like Maxwell showed us that electric fields and magnetic fields are just different aspects of one underlying entropy, the electromagnetic field. And the conservation principle of energy showed us that kinetic energy, chemical energy, gravitational potential energy, impact energy are all the same thing. And Einstein showed us that that thing, energy, is equivalent to mass. This is highly suggestive to me that we should at least explore the idea that in semi-classical gravity, entropy and energy are the same thing. So I think I'll stop there so that we have time for questions. I'm sorry I didn't have time to get into matter versus geometry. But so yeah, let's stop there.
So, question, remarks? Yeah? Mm-hmm. 1, 2.
I have maybe a somewhat naive question, but just where does time fit here?
No, it's not a naive question at all. It's a fantastic question. And it's something that I've struggled with and thought about, and I don't have a clear, well-worked answer for you. I can tell you a few things. So, a lot of the inequalities that I showed you in the semi-classical context, the relationships between components of the stress energy tensor and variations of the generalized entropy, these are all dynamical relations. These are relations that tell you that place constraints or place equivalence relations on quantities as they dynamically evolve forward in time. So a lot of the evidence, such as it is, that I'm suggesting should lead us to consider the possibility that energy and entropy really become much more intimately related here, is intimately tied up with the idea of dynamical evolution. It is the case also that even though we no longer have strict energy conservation in a generic relativistic space-time, we still have relationships between the inequalities that I've mentioned and the direction of the flow of time. So the generalized second law and also these other inequalities I showed you, insofar do allow you to pick out a distinguished future direction of time from a past direction of time in exactly the same way that the principle of entropy non-decrease allows you to do that in classical physics. Now, I mean, it's a very contentious idea that entropy non-decrease is somehow deeply tied up with the arrow of time. I'm not going to take any position on that here. But insofar as if one does think that there is an intimate relation between the arrow of time and the principle of entropy non-decrease, one has exactly the same kind of a conceptual structure relating them here. The other relationship that I mentioned early in the talk between energy and time, that one conception of energy in classical physics is as the generator of time translations, the generator of dynamical evolution. One does still have that in a sense in its framework, but it becomes much more subtle, and it's not as straightforward as Hamiltonian gives you vector field on phase space. It's rather more of the form that if you formulate general relativity and with quantum fields as matter, if you formulate the initial value problem in this framework, then there's a global quantity called the ADM mass, a global energetic quantity, which is related to the distribution of stress energy. And by some of these results, you actually can compute using the generalized entropy that generates the forward evolution of the entire space-like slice in an analogous way to the way that the Hamiltonian in classical physics generates the dynamical evolution for ordinary systems. But again, because we're now talking about a global quantity, you can't associate the ADM mass with any point in space-time or any region in space-time. It really is a quantity associated globally with the entire space-like hypersurface, that it conceptually becomes much more, to me at least, confusing and not entirely clear how it is that this global quantity generates local dynamics. So that to me is an incredibly interesting question. I would love for someone to figure out. So go work on that and tell me how this works.
Erik, thank you very much for your gorgeous lecture, for introducing us in this intimate relationship. But may I ask you for a very short period of time, when Slava talking several days ago about early dark energy, this period of time of few seconds after Big Bang, which is intimate relationships between entropy and energy?
Oh, so good. Yeah, that's a great question. So in fact, if these many of the results that I just very briefly mentioned and gestured at and sketched become really important in that period of time. So the calculations are too difficult to carry out with any exactitude and fine detail. We don't have really finely detailed models of the early state of the universe during those first few seconds. We have kind of crude, coarse-grained models, but it's exactly that kind of crude, coarse-grained model that we can apply these results to. And insofar as we think these crude, coarse-grained models we have of the very early universe are correct, it looks very strongly like you can characterize the dynamical evolution of the very early universe using either energy or entropy, and they both will work equivalently. So the very early universe has exactly the right properties that make these results directly applicable.
Okay, the next question, what was the first? Entropy of energy in this period. What was the egg and what was the...
I mean, to me, it's like asking which comes first, the electric field or the magnetic field. Neither one comes first. They both go together. They always go together. So they even if they don't turn out to be different aspects of one single underlying unified entity, it's still the case that you can't. Even in ordinary thermodynamics, you can't have energy without entropy, and you can't have entropy without energy, even though they're not the same thing. And the same is true here. You can't have energy without entropy in gravitational physics. You can't in semi-classical gravitational physics. You can't have entropy without energy. So whether or not they are different aspects of the same underlying unified thing, it doesn't make sense to ask which comes first. At least not to me. I don't see any way to say one is more fundamental or one comes first. They always go together.
Thank you.
Okay, so we have time for last question from Vincenzo.
Yeah, thank you very much, Erik, for also this wonderful lecture. I am thinking a lot about the fate of us proposed by Julius that dark energy makes the universe almost empty, and as you told, it is in a sense very similar to what at the end of the 19th century was the the warm death.
In English, we call it the heat death.
Yes, yeah, sure. Heat death. And indeed, the only hope for us was inside the black hole, I remember. But we know that entropy of black hole is proportional, as you proposed, to the surface of the black hole. So in a sense, inside the black hole could not happen anything relevant for entropy. You think that it is something definitive and so sort of definitive confirmation of the holographic principle of it is possible that inside black holes there could happen something different from what is reduction of the entire black hole to the surface.
Right. So yeah, that's a really great question. So sadly, we haven't yet been able to perform any experiments on the interiors of black holes. So everything I'm going to say is based on theory that has no really firm basis in empirical fact. But insofar as the event horizon of a black hole is in a sense one can make precise, not a locally distinguished surface. There's nothing really physically important happening from the purely gravitational standpoint at the event horizon. No purely local measurements I can make will determine whether I'm at an event horizon or not. An event horizon really is a kind of global structure in the same way that an ADM mass is, in a funny way. So insofar as that's correct, I personally don't see any reason to suspect that general relativity fails inside of a black hole, at least not until you get to extremely high curvatures, and you might expect quantum gravity effects to take over. So it seems to me that insofar as we can project our knowledge of general relativity into to these kinds of the parts of these systems that we haven't yet had any empirical access to, it seems to me kind of a most reasonable, certainly epistemically safest, but I think also most reasonable to say general relativity and quantum field theory continue to hold within a black hole until you get to regions of very high curvature. So I mean, there are these proposals like 't Hooft has to say that in fact there is no interior of a black hole. It kind of reminds me of Descartes' argument that if you have a box and there's a vacuum in the box, then there actually is no space in the box. The two sides just touch. And so 't Hooft's idea is kind of similar to that. And his arguments are based on the holographic principle, as you mentioned. I mean, I personally I think one has to be careful in talking about the holographic principle and its relation to these entropy bounds. So the motivation for 't Hooft was the first one to formulate something like the holographic principle back in '83, I think, early '80s. It was '83. It was early '80s, I think '83, and then Susskind picked it up in '84, '85, and they both made a rather large leap. So the Bekenstein bound on entropy, the Busso bound on entropy, very strongly suggests that for a given amount of mass energy, the maximum amount of entropy that mass energy can have is equal to the entropy of a black hole of that mass energy. You can't get more entropy associated with a given mass energy than the black hole of the same mass. That's an upper bound. But 't Hooft and Susskind wanted to make what I think of as a rather unmotivated leap to say it follows from this that in fact all the degrees of freedom inside say the kind of holographic surface of like an event horizon is equivalent to the degrees of freedom on the event horizon. And it's a bold conjecture, but I don't see any reason to believe that kind of reasoning tells us that general relativity should break down inside of a black hole.